So thank you, Molly. It's Friday the 13th. Good luck. So my name is Ariel Malicse. I'm currently an owner of the Malicse Holdings and also an adjunct professor at San Jacinto College. Used to work for a lot of oil companies and service companies in the past. So my talk today is about the application of quantitative facies analysis to sedimentology, stratigraphy, geochemistry of unconventional shale resources. I will be talking about how quantifying a facies, be it lithological, geochemical, or even petrophysical, can be used for practical sense in sedimentology, stratigraphy, and geochemistry. Actually, this QFA can be applied to almost anything, even what we call CL coloring. The results obtained from this very simple technique, because it's really very simple, is we can use it to reconstruct paleodepositional environments. We can quantify facies, and because we're quantifying something, we can obtain various statistics. Every time you have a number, you can do a lot of things. We can also use this for practical reasons. We've used it actually, and then I'll show it to you for predicting rock mechanic behavior, although I won't be going to that in great detail because those are all separate talks. And if I have time, I'm going to talk to you about geochems, how I apply this to geochemistry, and particularly for predicting the order of sequence, whether it's random or ordered using the Markov chain analysis. So the objectives of this study are pretty much the first part. I'll talk about QFA, which is quantitative facies analysis. So I'll be referring to quantitative facies analysis as QFA all the time from here on, to sedimentology, stratigraphy, geochemistry. The second part would be mostly geochemistry. And if I have time, I'm going to show a bit of Markov chain analysis as it applies to geochemistry, particularly XRF data sets. So I will not be reading each name of this one because when I was running this, I ended up eating more time mentioning the name. So I'm just going to skip this. And if I have time, so this study started in early phase when I was still at Shale. And we presented this in 2013 and presented it again and continues to gather more data in 2016 when I was at Murphy with the help of Core Lab Laboratories. So this is a continuing study as applied to quantitative facies analysis. So my talk will be divided, as I mentioned, into two parts. I will primarily talk about sedimentology, stratigraphy, application of QFA in the Eagle Ford facies. And then the second part is geochemistry facies as it applies to the West Texas Permian Basin. So I'm going to go through particularly for people who are not familiar with the Eagle Ford outside of this country listening, I'd like to go through some of the backgrounds of what an Eagle Ford is, go through some of the sedimentary facies that we have identified, and then I'll go to the methodology. So here it is. For the first part of the course analyzed belongs to the Eagle Ford Formation. The Eagle Ford Formation, hold on, let me just change my pointer here. The Eagle Ford Formation was deposited during the late Cretaceous, late Cenomanian to Turonian time. That's about 97 to 89.8 billion years ago. So the Eagle Ford was deposited, what we call the Bonorelli event, during a period of ocean anoxic event, a period of time when large portion of the oceans, particularly, have relatively low oxygen. Everything is relative here. And major deposition of organic shales and marls. The Eagle Ford Formation was deposited throughout most of Texas, shown here. Their composition does vary, for example, and that's usually demarcated by the position of the San Marcos Arch. Anything to the northeast part, the Eagle Ford tends to be clay-rich because of the deltaic system that we're fitting into the basin, whereas the southwest section of the Eagle Ford tend to be a marly calcareous type. So these are Coquina, Foraminifera, marly limestone here. So for this study, I use we were part, both at Murphy and at Shell, we were part of the Core Lab Consortium where they have a lot of cores. This is actually not updated. There are probably more than 37 cores now. But these were some of the cores that we used, plus four more from Murphy, uh, to reconstruct to pretty much do the quantitative facies analysis, the QFA. So to give you an idea, this is for those not familiar with the paleogeography of Texas at that time. So landward is going northwest or north, and as we go into the reef complexes, there are two reef complexes during the Cretaceous, the Edwards and Reef, we're going basinward in this direction. So the reason I'm saying that's because that has a major effect on the paleodepositional system. QFA is nothing but an extension of core description. It's like it's nothing more than counting. If you like to count, there it is. QFA is nothing but counting. So it's counting of individual facies. So this is just like describing a core, except for each facies, you know the top and bottom. So now you can literally quantify the orders of each facies. Just like when describing a core, I've been a sedimentologist since 1987. You describe the color and every feature that's associated with that facies, upper and lower contacts. And then, of course, you eventually generate your code description panel. So QFA is sort of just an extension of that. Of course, for many companies doing unconventional resources studies, it is more than that, right? We do biostratigraphy, XRD, all sorts of organic facies analysis and geochemistry. We also did a lot of rock mechanic data analysis on most of these cores, many of these cores. But for now, I'll be focusing primarily on QFA. So for the first part, I would like to just single out a few important facies in this study. There are about 9 of them, but with the purpose of simplicity, the important ones are the organic rich facies, which I call facies 1A and 2A. So these are rocks, the Eagle Ford that has present date total organic carbon or TOC of 3 to 8%. They have the highest TOC of all the facies. Calcite content ranges from 40 to 70% by weight, and the rest are mostly a mixture of clays, a bit of quartz, pyrite, and other feldspars and all that stuff. They are deposited during a period with lowest energies. These are mostly suspension deposits with occasional, probably small flow regime ripples coming in. Probably in a condition where oxygen level, dissolved oxygen level in the ocean was fairly low. I don't have the exact number right now. So mostly probably suboxic to an almost anoxic event. I don't know if there's really an anoxic event here, per se. The figure 2C is this ripple laminated Eagle Ford, the mostly calcite. And if you see this banded light dark, these are mostly type D ripples, are classified as 2B. So this is 2C. The 2B contains a little bit of TOC from 1 to 3%. So the dark color obviously is where your organic is. 2C generally tends to have little or no organic content, very low TOC, usually less than 2%. And then facies 3 are those I interpreted as fairly high energy traction deposits. In the outcrop, you will see most of these of hummocks or distal tubidites. These are made up primarily of calcite, 80 to 95%, and very low TOC. So what you will see is primarily a contrast between so these are your highest energy relatively, and these are your fairly low energy, high organic facies. Now, towards the Turonian time, the oxygen level starts to come in back, or at least increase more. And so what happens is now they tend to be biotubated. So 1B is another facies. So 1B and 1C are my biotubated facies. 1B contains a bit of TOC, 1 to 3%, a bit of clay mixed in, and calcite of 70 to 80%. 1C, on the other hand, is really light gray to cream, almost very light color. This is almost the typical facies you will find in the Austin Chalk. They have less than 2%, generally less than 1% TOC, very high calcite content. Both of them may have been deposited because they're now all being churned up by burrows, probably with a combination of suspension to ripple regime deposits in mostly slightly more oxygenated to even oxygenated conditions. So what is quantitative facies analysis? So this is, if there's any slide I want you to all remember, just this one. This is pretty much what it is. It is nothing but the cumulative amounts of a given facies per given stratigraphic interval. So it's what you're practically doing is just making a cumulative amount of any given facies at any interval that you want. So for example, shown here, so we're going to calculate, this is facies 3. If you remember, facies 3 is our storm deposits, the high calcite content, the highest energy, at least on this Eagle Ford. So what we're going to be measuring is the cumulative amount of facies 3 from bottom to top. So this is assuming this is the base of your Eagle Ford, and below this is your Buddha. So what we have here at the beginning, it's all, for example, 0 to 10 feet is all your facies 1A, your organic rich one. It is not until you get to 10 to 20 feet that you start getting facies 3. So the top of facies 3, so this is 10 feet, and the entire unit's already 20 feet, right? That makes facies 3 makes up about 50% of your total core that you have been counting, right? Including 1A. So that what you're doing is just literally counting the cumulative amounts of 3 relative to the entire sequence. So this plot in here, as you can see in the red one, shows you the cumulative facies occurrences. So the advantages, I think, of this one is a vertical cumulative plot per facies is that you can literally slice at various stratigraphic horizon, any horizon you want, and you get a glimpse of how much facies has accumulated at that particular phase. For example, at this point, I know I have 50%, and at this point, I have close to 60% of facies 3. The shape of the cumulative vertical sequence, this one, the shape of the sequence reflects the sort of a paleogeography of the study area. If I will not show in here, if you look at the more distal part, they all look the same. The middle part looks the same, and the more proximal region tend to look the same. It's simply because of the energy distribution. So certain facies like 1A, in fact, facies 3 disappears almost completely as you go below the storm wave base. So you practically all you have is almost like 100% of facies 1A, the organic rich facies. So that's very important. Also, what is critical in here is the inflection points, like this one here. The inflection points gives you sort of an idea when, if you think the facies is a reflection of the energy or whatever condition, that inflection point tells you when things starts to change. And you can see this basin work, throughout. So this inflection points here, for example, tells you at the beginning it's increasing in energy if that's how you want to interpret facies 3, and then from this point to that point, you see the amount of facies 3 dropping, indicating that your flow energy, if you think of it as an energy deposition, it's dropping. That is, it really depends on how you want to interpret the facies. So now I'm going to show you, this is an actual one of the core from there. And this one, I've divided into 4 units, the A, the B, the C, and the D. This is really up to the user of QFA where they want to do the division, but this is just how I did it, right? So if you look at 1, the black one here, the 1A and 2A combination, and 3, which is this one here, the red one, they're like mirror images of each other. When one is increasing, the other one is dropping. It's pure and simple. When suspension is increasing, it's probably because your traction deposit is increasing. So if you follow this through time, you can see literally, you start off with a lot of organic rich 1A, and then it kind of zigzags back and forth in here. And then from the base of B to the top of B, you sort of see a slight decrease in high TOC. If you look at the facies 3, which is the inverse of that, you can see sort of an increase. So here you can interpret that your suspension is increasing, decreasing, probably your energy is slightly increasing. So that's why you have more storm deposit. And then when we go from the base of C to the top of C, you can see now that there's an increase in organic content and it's a decrease on your halkite storm deposits. So now vice versa, right? Now you see, if you look at this as an energy demarcation, you can see that you probably your water is increasing suspension deposit, probably because you're decreasing your energy. You can look at it also in the form of what we call, if you think it's associated with the water depth, you may think of it as it's slightly deepening. It really depends, or however you want to interpret your depositional system. So why is this important? At the end, this cumulative phase sheet trend in the course studied. So what happens if one create an ISO percent map of organic phase sheet 1A? This is just ISO percent of when at the top of stratigraphic horizon A. So at the top of A right here, the stratigraphic horizons A is shown in the left diagram, which is this one here. The map on the right shows the ISO percent map of phase sheet 1A at the top of stratigraphic horizon A from all the cores we have studied. So the brown, if you look at the legend, the brown color has the least percentage of 1A, and the teal blue has the highest amount of phase sheet 1A. Again, this is your organic rich rock. The amount of phase sheet 1A, according to me, and it reflects the paleo depth of the marine shelf at the top of the horizon A. So brown areas represent area what I would interpret as shallower shelf, because I have more storm deposits here. And the paleo shelf gets deeper with higher percentage of phase sheet 1A. And that is as we go basinward, as you can see through here. So the paleo shelf does deepen basinward from northwest to about southeast into the paleo reef margins. What is interesting is that the shallowing is not as uniform as widthing. As you can see, there's sort of a peninsula in here. So then if you look at the slice of various slices of Eagle Ford facies at various horizons, the top of A, the top of B, at the top of C, and the top of D, as you can see through here, again, using the same color coding that we have in here, you can see the sort of the pattern of I interpret this as more of a paleogeographic information to me, at least, So if you look at the top of B, for example, this is almost like at the top of your Eagle Ford. They all look the same and sort of similar, and also not different. And they're also different, right? So if you look at this one, particularly at the corner of Webb, I think this is Dimmitt and Webb County, you see this, so something that's kind of protruding up here. And it is, in real life, this is an area where we actually have a little no Eagle Ford, and this is an area also where we have, if I've shown you the facial 1B, the bioturbated section, this is also the area where you have a lot of those accumulating. So this was sort of a paleo high, if you think about it, during much of the lower Eagle Ford, as well as some of this area. So that's one of the application of quantitative facies analysis. Is you can literally, because you're quantifying something, you can create this cumulative distribution per core, and then slice it at various interval and create whatever ISO percent map, which and you can interpret it the way you want, right? To me, it's an interpretation of a change in flow regime or a depositional system. So that's good, but is it practical? One of the, yes, because anytime you quantify something, so one of the practical application of this, and we found this very useful for our development geologists, is when you make a ratio of the incompetent facies. What is incompetent facies? These are your 1A, 2A. These are the rocks in the Eagle Ford that contains higher amount of clay. So I hate to use the word ductile, but yes, there's slightly more clay and slightly more ductile, whether that's inapplicable, obviously, versus the competent facies, which are your calcite rich. These are the rocks that have, generally speaking, a lot of calcite. They're hard. And so the paper by Farrell and Morris on APG and Smart et al. 2014 this is the reason why I did this, right? for the study by Ferrer and Morris, for example, shows that if you know the ratio of your competent and incompetent to competent bed, you can more or less, they were able to see how natural fractures and faults develop as a ratio of those, right? And the detail obviously is in their paper. But these are for mostly predicting natural fractures. They apply this they apply this in South Texas, in the Balcones Fault Zone region. Now, if you're going to be looking for application of the incompetent to competent facies on hydraulic fractures, when you frac these rocks, I would suggest that you look the paper by Smart et al. In 2014. I can provide this to you if you're interested towards the end. So this is one of the, because we are quantifying each one of these facies, we know exactly how much we have. So I'm going to show you a practical one of the cross section, just to give you an idea of how do they look like, you know. So I'm going to show you a cross section from 1, 2, 3, and 4 wells in here running north south, and I'll just show you, how they look. The incompetent to competent facie ratio looks like. So here it is, and the scales are right. I lost my 8 miles, 18 miles. So they're really far apart, but that's how cores are. You don't really get them in close density, except Shale, they do that. So if you look at just one unit, what you will see is, for example, unit A and unit C tend to have, so by the way, the scale here is you have more incompetent facies ratio as you go to the left, and you have more of the brittle competent facies as you swing to the right. So this is the unit here is, I kind of inverted it. So that way it's skinnier when you have more shale, and it kicks more to the right when you have more limestone, right? So if you look at unit A and unit C, that's where the unit that seems to have a bit more of the organic or facies, right? This A and, whereas if you're looking for, if you're targeting for, or if you're interested in more calcite-rich rocks, it would be unit B and unit AA. So in this case, obviously, this is, since most of the development usually targets EA or unit C. In reality, many companies do that simply because most of your organic materials are in here. But it's nice to know how they also vary both vertically and laterally. As you can see through here, 4.6. This is your incompetent to competent facie ratio as you go from left to right. But that's nice. But it's not too practical on sometimes also on a field scale, because in a field scale, you really want to be able to quantify something that are in close proximity. So what we have done, and this is with I was working with John BALUMER, our petrophysicist then at Murphy, when we were both still working at Murphy. So what we did was we converted, again, we remember we quantified each of the facies in the core. So what we just did is convert that to petrophysics facies. So now instead of having 9 lithofacies, we converted it to only 4. So we kind of just simplify this. So A would be your most organic rich facies, and B would be slightly organic, but well, actually lesser organic, but lesser calcite content. So this is how we divide it: A, B, C, and D. Just remember A as your more organic rich ones, and the color coding right through here, because the next slide you will see is a 2-dimension representation of the petrophysical facies. So,
hey, Ariel, you've got about 6 minutes left, okay?
Okay, there we go. So I'm gonna probably skip the geochemistry now. So a 3D geologic model using Petrel was created using this petrophysical facies. The figure shown here, however, is a 2D cross-section of the various petrophysical facies. So this model is then used to create geomechanics and fracture models. So if you can see through here, the yellow ones are your organic rich facies. This blue and gray ones are, particularly the gray ones, are your calcite rich facies. So we created a 3-dimensional model of this one. And what we did, so I suggest that you look at the paper that was written by the people from Premier and including us. So we're co-authors on this one. So this is one of those approach when we actually use this approach and tied it up to reservoir engineering production data to predict hydraulic fracture propagation, reservoir connectivity, and eventually to make suggestions on the type of completions that we will apply to any given wells or future wells that we were working at that time. All of this are, by the way, described in this paper. So I would like to, I'm going to cut my talk now because the other geochemistry talk takes another, probably another 10 minutes or so. So this is where I end my talk.